So now we're going to discuss about the pumps. We discussed before regarding the Francis turbine. Pumps are similar like Francis turbine, but in the opposite case, which is means the water inlet from here, not the inlet from here, and go out, while it is taking a kinetic energy from the runner and going without guidance vanes, with the violet case, increasing the area and decreasing the velocity in the benefit of increasing the pressure, which is the head of the pump. Okay, it is the similar case while the water is enter here in axis direction and ensuring that the water velocity is just vertical to the plate or vertical to the rotation speed. So V1 is equal V flow 1 and it is equal for sure V flow 2 because it's not never change. Okay, and because we know there is a rotational velocity in this direction, so we know like before that the relative velocity is the rotational velocity minus the x direction or the component in the rotation velocity. An example, as we discussed here in the Francis turbine, for example, we have this velocity. So a relative velocity, which is this one, in its x direction or in rotation direction, plus u is equal to the x component or the rotation direction component for v. Same concept. We don't have an rotation direction component for v1, so the x or the rotation component of vr1 is equal to u1. And when it's go out, v relative velocity go out with the same angle of the plate, stays the same because we know it is rotating like this. So this RV plus U in vector basis, of course. So this will be like this and this will be like this, equal to the velocity 2 in the rotation direction, which is this one. Okay, so based on this one, we can know what is the velocity component. Okay, and the velocity component in rotation direction for V2, it is the wiggling velocity or tangential velocity. Apply the same concept, this general rule, wiggling velocity multiply U2 minus wiggling velocity 1 multiply U1. We know that there is no wiggling velocity in 1, so the power per unit mass flow is equal to wiggling velocity at the exit multiplied by U. Use, of course, any triangle calculation to get, if you have VR, if you have U, if you have whatever, to get what is velocity. Okay, so the head, it is this one divided by G, so it is wiggling velocity 2 multiply U divided by G. Okay, this one is really theoretical head. So, but we know there is losses like what we discussed before in Francis turbine. Sometimes the water is not getting in x direction or it is vertical on the rotation velocity. Same, maybe the water is not going in the vertical direction of the, maybe it is a little bit shifted, so there is a losses which we name shock loss. Okay, if you have a shock losses, so it is what is the design flow minus what is the actual flow, all squared multiplied by k, and k is a design loss or shock factor, which is we'll get the H loss due to the shock. Okay, it is very easy, this one. Okay, and also we have another losses like the mechanical losses regarding the shaft, the friction of the shaft, etc., which is a mechanical losses itself. Also, it is very simple. It is what is the shaft power I'm giving, and what is the power what I'm getting from giving to the pump, which is rho GQ H. H is not written in clear, but here's H. Okay, so this one divided by, of course, this one is way bigger, so we'll get mechanical losses. Okay, there is another losses which is named manometric losses. The manometric losses is a friction loss, yet it's not due to the shaft, it is due to the friction loss inside. Okay, so its definition is what? Its definition is H minus, oh, which is, we name it available head, or what we are getting theoretically, minus the friction divided by what we are getting theoretically, and this is ideal. So is ideal is eta manometric equal 1, and the available head is equal to sigma or slip factor multiplied by the H theoretical. We're going to discuss what is slip factor. So this one is the H theoretical. Okay, so this one is the H theoretical. This is the first loss with K multiplied by Q squared. And also for the friction, it is this one, K, another K, multiplied by what? Multiplied by also Q squared. Now we have another loss which is named slip. The slip, its definition, it is acute to the movement of the moving of radial motion of the plate as leading edge increase the pressure, trail edge decrease the pressure. What is all of this? It is very simple. Because the blade is moving like this, so the leading edge having more pressure than here, and we know that is pump is giving head, so this point head is less than this point, so water start to circulate like this a little bit, which with a slip, with a small layer going to circulate like this. So even while we know that there's the pressure getting circulated like this, sorry, the flow going to circulate like this, so we know also because the pressure here is low and the pressure here is high, so when the pressure is high and the pressure is low, which is can be written like this, which is when the pressure here is high, so that means the velocity is low for the same injection of energy. So the kinetic energy here will be low and the kinetic energy here will be high because the pressure is low. So the distribution of the velocity between the plate is not equal. So this is a losses, and this losses is defined as sigma, which is the slip factor. Just to highlight, if we assume an ideal flow with non-frictional at all, zero friction, so there is no any friction here, there is no any head for still, and there is no shock, that means all angles is totally perfect. So still the pump going to have losses due to slip. So if there is no friction at all, and if all angle is correct, still due to slip, due to this action, the rotation motion itself, there is. Okay, so how to calculate the slip? Slip, it can calculate by an equation or a guy who write Stanist's formula, which is defined as approximately 1 minus this ratio, which is 0.63 multiplied by pi divided by number of plate. So while we are increasing the number of plate way high, this term is become 0, so this equal 1. So H theoretical, which is this one, equal H available, which is equal here. Okay, so the resultant, by the way, the resultant here when VW of velocity wiggling outside, it will be reduced while you have a slip factor, and the slip factor is equals 0.85 minus 0.2 from this number to this number. Also, by the way, the slip factor can be, as you can see here, h equal v w Whirling velocity 2 multiplied by 2 divided by g, just to be in the picture, because we know h is equal sigma or slip factor multiplied by h theoretical, which is this h theoretical. Also, we can say that is because this one is constant for a certain rotation of a bump, and this one is constant, so we can say that nu, it is not written here, but nu whirling velocity is equal to theoretical or whirling velocity multiplied by the slip factor. Okay, okay. Now let's study what is going to have. Based on here, we know that is head and q. So q is equal area multiplied by velocity of what we have here. So theoretically, in a way or other, because when you do triangle calculation, etc., to get the VF flow, etc., 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 whatever, so still you don't have any power to the velocity, because you want to change from this one to from whirling velocity to V flow, because here V flow is vertical, is the vertical component of V2, and V2 equals this one minus this. Do some manipulation in triangle, still you're not going to have head in equal to power of 2 or 3 or 5. It will be equal to power of 1 to the velocity. So it is a line. When you increase the flow, you're decreasing the head you can get. Okay, for a certain power you are giving. Okay, okay. This theoretical. Now we know that is head, which is due to slip. It is sigma multiplied by head, which is will act like this. So due to the slip, it will act like this. So while you're increasing the Q, you are reducing the head from here. Slip equals the slip. Okay. And the same concept also, if you have shock, it will make the losses, the losses will be like this. And due to the friction, which is a manometric, it will create like this. If you make sum this one, minus this one, minus this one, minus this one, you will take a curve like this, which is normally the curve of a bumps. This is just how if you start to put. Okay, okay. Now let's discuss about one point. It is applicable for fans, pumps, whatever you name it. It is applicable for all. About the backward plate, radial plate, and forward plate. Which one is better? When to select each one, and etc. See, the rotation is in this direction always. And we are not going to study this part because we understand the head, which is going, it is only depending on here. So let's check the backward plate, which is similar to this one. Backward plate, which is mean the plate angle is less than 90. So VR, relative velocity out, is like this. And you know that is u in this direction. So V2 will be in this direction. Of course, if u too much, so this one will go this too much. So whirling velocity will be this part. Like here, whirling velocity will be this part. It's not a big deal if it is like this, or u is big enough, so it will be like this. Still, what we are trying to get, that is whirling velocity is always will be less than u. Okay, so whirling velocity, like here, it is less than, always will be less than u. And based on this, just will write it like this. We'll go later on what we are doing here. Okay. Okay. Now, if we are in radial, that is mean VR is vertical. So VR is vertical. U is like this. The blade angle is 90. And V2 is like this. So whirling velocity is equal to U. Whirling velocity is equal to U. And if it is forward curve, so it is like this. Beta or blade angle is over than 90. So it is like this. So whirling velocity is bigger than U2. So this is the three cases. Okay. Based on the above, that in case if I have a radial flow, which is mean water enter smooth, gone out smooth. So water enter smooth, gone out smooth, which is mean nothing has been any clash. So we can assume that there is no any shock because it is enter smooth, gone smooth. So H theoretically will be a line like this. So this one will be a line like this. And again, if we start to say that is, which is K2, it is 2 here, the shock itself, okay? And if it is in case of backward, which is mean K2 is bigger than 0, and if it is forward, which is K2 is less than 0, so forward curve will be like this, and backward curve will be like this, which is mean increasing the flow will decrease the head, and here increasing the flow will increase the head. Okay, if you try to combine this to get the actual, combine all of this to get the actual, you will find that the radial, it is going like this. Forward curve, it is making like this. And I'm speaking about the power, by the way. So this is the radial power, and this is forward curve power, and this one, which is in the orange color, is backward curve power. From these curves, you will understand in case of you having more flow required, power needed or increased, and in the same case, if you have more flow required, power going to increase, and in the same case, if you have more flow is required, it is less power required. I'm just taking what I can see. In the opposite case, at the part load, which is if I am going to do it at part load, if I am going to select forward plate, I am going to select the optimal power. But if I'm going to part load, which is less flow, it will take more power. And if you are needed more flow, more power, and less flow, more power. But if you checked the radial, less flow, so the less flow, less power, and the backward curve, less flow, less power also. So this is disadvantage for the forward curve. That is mean It needed very high power in both cases if you are in part load and overload, which is forward cave is not ideal if you have an overflow or if you have a part load, because it will require more power than the optimal what you need. And even if you check for the flow itself, you don't want to select it here. We're going to discuss this later. That is, it is preferred to select after, not here. Why? You can select, by the way, this point even is corresponding with 2 points, but later I'm going to state why. But it is, you cannot run in this point. You can run in this point, but you cannot run in this point. However, it is preferred to take a line like this and only select here. This is regarding the flow, and this is H and this Q. So we can say that is backward blade is very good at part load, as it is self-limiting characteristic, even the radial one. And same as overflow, also as the overflow. Radial at the part load only, but at the overflow it has no any self-limiting characteristic. And also the forward curve is, which is this one, you cannot select here, because if you have a certain flow, see a certain flow, a system curve like this, so you have a certain flow, so you have a certain head. But remember that is you was running in a load and you're going to go to the part load. So now the line having this pressure, when it is like this, and you are returning back, see, when you're returning less and less flow, you will have a reverse flow coming to you. That is why you should not select in this one. Again, if you have this flow, this system curve, then you start to open the valves. So the system curve start to go in this direction. While it is going in this direction, the pressure required for the system should be less, because you are coming from high pressure then to low pressure. But if you are coming from here, from low pressure going up, so the pressure required is more to run more flow, which is create a high pressure after the pump, which is will create a back or a reverse flow. So that's why even in the fans, we are never select before this, we never run before this one. Always we are going to run here because we don't want the reverse flow. This is another point about backward or forward. Okay, when we're using a forward fan, we are using a forward plate fan, or if we need really a high pressure. We need a high pressure. How? From the curve. See, this curve is here, this curve is here. So we can get a high pressure with the forward curved plate. Okay. This is from the control volume. We already discussed it before. That is, if you have point, it is about the cavitation. If you need to check the cavitation for the pump, but we're going to discuss it in detail regarding the cavitation and Thomas number, and also the net booster suction head available and required. But a small recap: apply Bernoulli from point to point. Try from the tank. Try here. Put Z here is the datum. Then voila, you will get everything. So it takes the tank Z is datum. So this is one. So this is equal plus H friction. Manipulate left and right. So you will get pressure 2 here, which is the pressure before the pump. So the pressure before the pump equal the velocity component, the kinetic component, the potential component plus the friction. Please ensure that is the pressure if you multiply by rho g, this term. So ensure that is the pressure 2 is bigger than the vapor pressure, and if it is less than the vapor pressure, you will have a cavitation. This is a normal case about the cavitation. Okay, so you need to check, but this is a point about the cavitation, by the way, but yet we're going to know it later. There is something about net positive suction head available and required, so pump have a higher margin or needed a more safety to run. Why? We're going to discuss later. That is, inside the pump itself, there is a cavitation can occur, which is mean if your pressure here is above the vapor pressure, it's okay, safe for the pipe, but when the water run here, cavitation will occur because the moving itself, because you're increasing the velocity, so before increasing the pressure, so a cavitation can happen on the plate. Okay, so cavitation condition to happen before the pump, this is the equation. Yet even if this one over than the pressure, vapor pressure, still in the pump can happen a cavitation. We're going later to discuss it. Okay, let's discuss now some points. There is Thomas cavitation parameter. You can apply, it can be applied for turbine, for pump, for whatever. It is defining can a cavitation happen or no. Same equation what we've done here, it can be done for turbine, but turbine always we have high head, but pump always you are having low head. Okay, because turbine always you have high head, so it is never happen cavitation here, but cavitation can happen here. So Thomas cavitation parameter can be applied here. Thomas cavitation parameter can be applied as a suction. Okay, so at the turbine, after the turbine is at the tube, at the pump, at the suction. Okay, what is Thomas? Let's check what he's saying. Thomas is saying very simple concept, what we discussed before, that is B must be one, if you drive the tube, B1 should be equal, should be bigger than B vapor, and based on that, he start to put, that is the kinetic velocity minus the friction velocity, and he name it as sigma C, which is critical cavitation parameter. Same like what we done here. So he took this one, the kinetic energy, and he took the friction, and he just put it together. So it is, sorry, it is kinetic. Here it is, of course, here because from this point to this point, but if you remember in the drafted tube, it is from this point to this point. So this point is it's equal to 0. That is why this one in minus, this one in plus, but in pump, both in plus, both in minus or both in plus, whatever. Okay. So in turbine, so this one minus this one, which is, we name it like this, it is equal what? Equal pressure here, OG, and pressure here. So pressure here OG, pressure here OG, and that this is the height, what we discussed before. Okay, so he can write an equation, simple one, which is, okay, the same equation, B2 OG minus B1 OG minus Z. Yet he said that this one is sigma C multiplied by H, and he writing that is H is the head of what is going to, the resultant head for that equipment. Okay, and he can get this number. Then Thomas start to state, this is for Thomas, by the way. Okay, so we start to state that is this sigma actual, or whatever he's going to get, but not B1. He assumes that is here already a cavitation happened. So critical cavitation parameter is a normal one, or the actual condition that we have. And he said, okay, I assume as Thomas, that is here a cavitation already happened, and I'm going to calculate QC. So he start to say that is sigma should be bigger than sigma C by anyhow to avoid cavitation. Why we are trying to get sigma and sigma C? Because of this. Sigma C, which is a parameter of which is a parameter for the pump B1 and B2, it is a function of NST. NST is the specific speed for the turbine. Specific speed of the turbine is dimensionless analysis, which is mean it is a pi. So if this one is a function of a pi, that is mean it is a constant for any scale of the turbine. This is the beauty of the critical parameter. And this one is a calculated. So you can calculate and you can get sigma Thomas or Thomas cavitation parameter. You can calculate it and you will check what is specific speed of the turbine, and you check what is the family it have. It is one model, so you know already if the turbine get bigger or less. You know what should be sigma C by anyhow, because this one is known. You calculate it, so you can get sigma C while the turbine. Even so, even you can decide based on the selection of the turbine. How? See. Before to go this one, I'm just showing to you the specific speed to know what is the best efficiency for a turbine or a pump, whatever. You know when the specific speed you start to calculate specific speed, it is a pi number, which is doesn't care what is happening inside the turbine or the pump. It is a pi based on Buckingham biaxiom. So it's rotation, flow, and G and H. It is a dimensionless number. So when this number get increased, you can select all families of Francis turbine. It is between 0.4 to 2.5 approximation. It is the best efficiency in this area. And Belton is best efficiency here. And Kaplan is best efficiency here. So based on this, you can select based on specific speed. You can select, okay, I'm going to use Kaplan turbine. Good. Because they have very high specific speed. Then you will ask yourself, I know the specific speed and I know the turbine which I'm going to select. Okay, is this turbine is safe or not safe for cavitation? Same concept. You will find QC, and for example, Francis turbine, Kaplan turbine. Then you will have here, you will get QC. When you have QC from this one, you calculate sigma C. You can calculate sigma Thomas and check is Thomas cavitation parameter bigger than sigma C or no. If it is bigger than sigma C, voila, you are safe and the turbine is safe. Okay, what about the pump? Pump is the same concept. Pump, when you increase the specific speed, the best performance in radial, then mixed flow, then the axial flow. Radial, which is mean centrifuge pump. Mixed flow, which is mean part centrifuge plus part axial. Axial, you know, it is axial pump, any axial pump, which is like an impeller, for example. This is like this, an axial pump, okay, and this is fully centrifuge. Okay, so based on this, you can select which pump you're going to select. You already selected the pump. Now you are need to check something named suction specific speed, and it is like the specific speed of the pump, but bear with me. Now we know that is net positive suction head, which we didn't discuss it yet. No. Interview power post function cavitation. Yeah, we'll discuss this one first. So we know that is net positive suction head. It, as we discussed, that is same what we done before, is atmospheric pressure. Neglect this one for now. Neglect this part. So the static head as a suction minus the losses minus kinetic energy return back. The static head plus the friction plus the kinetic. It is the pressure where before the pump. So static plus pressure, of course with minus, always minus. So it is static, but of course the static will be in minus because it is suction. Maybe the tank above the pump, so the static will be in plus, by the way. Okay, so static minus the friction minus kinetic. It is the pressure at the suction. But it is better when you deal with pressure vapor to use absolute. So add the absolute, add H atmosphere, which is we are not gauge pressure. And all of this should be what? Bigger than H vapor. But we removed H vapor from this side to this side. And we named all of this item is not positive suction head available. This is the available suction head. Okay? And it should be bigger than net positive suction head required for the pump, as we agreed. But inside the pump itself, there is some cavitation can be happen. Okay, let's return to this what we was discussing. So now net positive suction head available, we know it. Now net positive suction head required is equal to n q square over gh over 3 over 4, which is net positive suction head required over 3 over 4. What happened? What is this one? It is very simple. It is that the suction specific speed, it is just a dimensionless analysis. Dimensionless. It is just a dimensionless analysis. But we calculate that suction specific speed when h here is at the vapor. Okay? Which is equal this one. H at the vapor. Then we calculate h, then we get suction specific speed. And at this speed, cavitation will happen. So at suction specific speed, at net positive suction head available, it is in Q, same like equation, but available. Okay. So if this one suction specific speed and suction specific speed for required, you check it, and there is curves of course for it, and you find that is your specific speed is matching this one, so you're going to have a cavitation. Okay, which is a property of the pump. However, you can go directly, and calculate with the safety factor as per the answers. Like here, as per ANSI 9.6.1 is stating like, okay, required should be bigger than this one with this number, and if it is stainless steel and if it's cast iron, etc. It is ways to know which one you're going to do. Okay, let's close also cavitation. It's a chapter of cavitation now, better than later. We discussed about this one, atmosphere minus vapor plus H static rho g over half of v square should be bigger than, which is the cavitation number, the Thomas number. Okay. Same, we're going to repeat it. I don't want to repeat it again. but we just discuss it here. That is, this one should be bigger than this one, and this one is same like this one, but it is written as vapor. It is the same, just here, which is written atmosphere plus minus vapor, it is which is taking account the absolute head, but it is the same concept. Okay. Okay. What's the type of cavitation what we have inside the pump? So even if there is no cavitation in the suction, but still in the pump some cavitation going to happen. Why? Because maybe 6 reasons. 1. Tip and hub vortex. 2. There is a sheet cavitation. 3. There is a bubble cavitation. 4. There is a root cavitation. 5. There is a propeller hull vortex cavitation. And 6. There is an unsteady sheet cloud cavitation. Okay, let's check the tip and hub vortex cavitation. Tip and hub vortex cavitation, it's occur at the plate tip or hub. Okay, tip or hub. Okay, of the propeller for the plate itself. Okay, generated from the core itself of the vortex. It is like this. You see, when this one start to rotate, you see this one, there is a vortex going to happen. This vortex will create a low pressure here, which is can be when it is more and more velocity, this vortex can reach till here and will create less and less and less pressure. Even here there's no cavitation by the way, and there's a suction, and less pressure on the plate, which is will create a cavitation. Of course, it will appear first at a distance, then when high velocity it is come near, and then it will be stronger. Okay. 2. The sheet cavitation. The sheet cavitation occur when the pressure distribution has a strong adverse pressure gradient, which is mean separation. It is not clear maybe, but it is a separation. Adverse pressure, it is separation. Why it is happen? Why is separation is happen? Separation is happen, as we agreed before, if you have a flow like this, and for example for the volute case, or the case itself or whatever, but the pressure already it is increased because it is a pump. By anyhow, even the shape is okay, but the pressure is increased, and the pressure here is low. We agreed some separation going to happen like this when the flow is going like this. Even it's not the case, even the impeller itself, if the impeller itself is like this, and this is area is less and this area is big, so also when it is go like this, some separation can happen like this because the pressure here is high, pressure here is low. Okay, so let's retain. Why this separation happen? If you case you have a very long plate, yes, it is logic. If you have very long plate, because as we agreed before, in case of the plate stop here or stop here, and the separation will happen here, so you don't have a separation. But when you have a very long plates, separation can happen. Okay, let's say that is separation happen. Okay, the separation when it is happen and that vortex happen, this is increase the velocity here, and this is going to increase the velocity here, which is will reduce the pressure. Okay, when it is reduce the pressure here under the vapor pressure can act as a cavitation. Okay, it is start at the leading edge of the propeller blade when positive angle attack, agreed, positive angle of attack, which is mean this shape is a positive angle of attack, or like this, in front of, which is create sigma, and in the front it will be negative angle of attack. Okay. For example, if you gun here, yes. For example, if another plate is like this, so here is negative angle and here it will be positive angle. Okay. But however, we understand the concept here. Okay. Okay. Or if you have a plate itself and the flow is hitting the plate. Let's see. If you have a plate like this and you have a flow and the plate, let's say it is rotating or moving or whatever, but you have a positive angle of attack. So like this is positive and like this is so opposite, like this is a negative angle of attack, which is mean alpha in negative, and this alpha is positive. When alpha is in negative, so flow is going like this, and here is separation going to happen. So see, the flow will go and will make separation because the diverging part is here and this is converging part. Okay, so based on this, cavitation happen at the at the face of, this is the face and this is the back, by the way, at the face of the plate. And of course this one, as we agreed, sigma is delta B over kinetic energy divided by m dot. And if it is having a minus angle of attack like this, by logic separation will happen here at the back face, which is will happen here. Okay. Okay, now the bubble. The bubble is due to pressure distribution, which cause high suction pressure in mid of chord region of the blade, as when blade section thickness angle of attack is small. It is like this. Okay. When you have a flow going over the plate, and remember that which cause high suction pressure, the chord region of the plate as with a, yes, thick section. So when you have a very thick section of a plate, so the plate is very thick, so some of the flow will go up, some of the flow will go down. But you remember, according to the shape of the plate, some of the flow which is going up, increasing the velocity here, like aeroplane aerofoil, plane aerofoil. So here is the pressure going to increase due to the increasing of the velocity. So decrease due to increasing the velocity, and here will be less, but increasing the velocity and reducing the pressure here will create, if the pressure is less than the cavitation pressure, so it will create a bubbles based on the pressure distribution, of course, according to the shape of the airfoil. This is a bubble. Okay. The root. The root cavitation, we are reached to 4. Root cavitation, it is a cure at the plate root, which with shape of wedge or at leading edge at the plate itself, due to what? Horseshoe vortex developed at root and its inclined shaft. What is this? It is to explain it that imagine that you have a plate and the start of the plate. So again, delete. You have a plate and the start of the plate, the root of the plate, the start of the plate. Okay, so the start of the plate with shape of wedge. What does mean wedge? Wedge, which is mean it is like this. which is mean here it is curved. It is curved itself here. Okay, so the blade is curved in a way at the root. Okay, so which at top of the which its leading edge at the blade itself due to horseshoe vortex. That shape of the blade will create a horseshoe vortex at the root for the inclined shaft. Okay, so it is related to the shape itself of the blade. It is can have it is happen. What is this? At uh, controlled pitch propeller. What is controlled pitch propeller? And see, when it is happen, it is happen if you have this is a pitch, this one. So if you have a controlled pitch propeller, which means the propeller can rotate a little bit and to decrease the pitch or increase the pitch. So can rotate in each axis like this to change the flow parameter and the head parameter. When you do like this, you will make that twist, which is creating that horseshoe vortex. Okay, so it is happening in this kind of propellers. Now the propeller hull vortex cavitation. It is based on, imagine you have a propeller or a blades rotating and there is a casing here. So this casing or between the propeller and of course you cannot keep the propeller touching the casing, there is some. So when it is moved, there is a vortex happen here in this area. When it is moved, so there is vortex happen here in this area. So it is occurring a vortex between the propeller tip and the ship hull or the case itself due to small tip clearance because of the turbulence and the stagnation of this point. Okay, here is the stagnation point, by the way. Okay, so this is stagnation point, this is 0 and this is very high speed. So what will happen, it is making a very high turbulence here due to the difference between very high and 0. So we'll create a very high vortex, with the vortex more velocity, less pressure, cavitation. Okay, the cloud cavitation. Cloud cavitation, it is a sheet flow. Where is the sheet flow? It is the sheet flow. It is due to the separation, but it is a very strong sheet flow, steady one, and if it is happen, the entire plate having a full cavitation, and this is very serious and need to take an action. So this one is a type of this one. So like this, the pumps and cavitation has finished. Later we're going to discuss about the centrifugal compressor and wind turbine, etc.